And like I said, we're going to do this as part 1 and part 2. So if you would please label your, or title your paper that. So no, I'm not going to do everything today because that would just make everybody want to cry. What's that? What you need? Yeah. All right, so I'm first going to start off with some of the ways that we measure how climate has changed over Earth's history. This has a name. It's called paleoclimatology. Paleoclimatology. You could go into it if it's your gig, like you wanted to. I don't know. Okay. Alrighty. So it is a thing. So starting with that, so we use indirect. Obviously, it has to be indirect. Indirect measurements to determine temperature of atmosphere. Okay. Now, sometimes Ms. Johnson abbreviates things. Do you guys know what I'm writing here? Okay, good. All right, so I'm going to go through the different examples, and so I'm going to start with the very first one. And this one's kind of weird. We talked about these guys back freshman year. We talked about protists, but of course you slept since. But we can study these protists that have shells, and they have a funny name. Foraminifera. Those shells accumulate. Sorry, that's spelled wrong. In sediment. So those shells accumulate at the bottom of the ocean, and sediment at the bottom of the ocean. Different species have different tolerances, temperature tolerances, so we can determine what the temperature was based upon which species is in that particular layer of sediment. Okay? I got that. I don't know if that's going to work. Mm-hmm. So different species with different temperature tolerances. That's going to help determine the possible temperature at that time. So that's one way we can measure. Another way, which is really kind of cool, they're called ice cores. Let me see if I can get you a picture so I know, so you know what I'm talking about. Sorry, I'll leave that. So basically what we can do is we can dig deep into the ice and kind of pull out a cylindrical core here. And just like sediment, the oldest gases are at the bottom and the newest are at the top. And then we can examine that. And so that's one way that we can determine what the atmosphere was like. So using ice cores. So those are air bubbles in ice. can indicate the composition of the atmosphere at that time. And just like sediment, the oldest is at the bottom. These ice cores can date all the way back 500,000 years. We know that about 400,000 years ago, approximately 400,000 years ago, the atmospheric CO2, we use this data to figure this out. Atmospheric CO2 was approximately 300 parts per million. And that's how we got that data, is using ice cores. Parts per million. 407 parts per million. That's a lot, though. Parts per million. So not only carbon dioxide, we can also look at isotopes. Okay, so one particular isotope is oxygen 18. So changes in isotopes. We just finished talking about half-lives. So we have oxygen 16, which is kind of the normal one, because oxygen has 8 electrons, versus oxygen 18. The more oxygen 18 there is, the greater the temperature is. So when we're looking at those ice cores, if there's more oxygen 18, we know that the atmospheric temperature was higher. All right, so I'm not going to do the other ones. I want to switch gears from measurements and go to naturally occurring changes over time. So naturally occurring changes in Earth's climate over time. Like, why did it happen? Obviously, when I say natural, I mean non-human caused. So what are some things that happen? So we had volcanic eruptions. That would have caused a decrease in temperature. Why? Yeah, ash. Very good. Meteor strikes. Same thing. Changes in, yes. Solar output. So the sun does not produce the same amount of energy all the time. So there have been times when the sun has been cooler. Changes in Earth's tilt and orbit. Any change in Earth's tilt or orbit would change the rate of insulation, sorry. There have been changes in wind circulation. Obviously related to changes in solar output. And if there's change in wind circulation, then we know there's change in ocean circulation too. Because the wind circulation, global winds control global ocean currents. Changes in amount of ice, polar ice. And then changes in atmospheric greenhouse gases. All of this naturally will change the climate. Naturally. If you guys have a different color, that might be helpful. Like 2 different colors. In a minute. We're going to draw a graph. So, obviously, when we have seasons, there's going to be a change in atmospheric CO2. So, in the winter, do you think atmospheric CO2 goes up or down in the winter?
Up.
Right. Why does it go up?
Because more people are burning stuff just to heat themselves.
There's that. But what happens with photosynthesis? Is there the same amount of photosynthesis?
It decreases.
It decreases. So in the springtime, in the summertime, there's more photosynthesis, therefore less CO2. So it's almost like the earth inhales and exhales. Okay? So you're going to get more CO2 in the atmosphere during the winter months and less during the summer and spring months. Okay? All right. So let's talk about that fluctuation. I'm going to another page. You don't have to. You have plenty of room. All right, so over the past 900,000 years, Earth has fluctuated between atmospheric cooling and warming. The cooling often led to ice ages. The warming melted ice and raised sea levels. Temperature and atmospheric concentrations of CO2 are directly correlated. So as one goes up, so does the other. So drawing a graph real quick. And it doesn't have to be perfect. I just need you to get the gist of it. So I'm putting atmospheric CO2 and global temperature here. And I'm going to start here at 800,000 years ago. And I'm going to end at now. Okay, so with atmospheric CO2, I wanted you to understand the reason why I'm going up and down like this is because in the winter months, there's more CO2. Spring months, there's less. So it's not a straight line. It's got to be up and down. Okay, so I don't want you to be like, what is she doing? So it doesn't have to be perfect. I just need you to get the general look here. And then obviously now it's way up there, right? So that's our CO2 level. And then I'm just going to choose a different color. What are you seeing with temperature here? Huh? Temperature's doing what? It goes right along with concentrations of CO2 in the atmosphere. So the more CO2 in the atmosphere, the higher the temperature goes. All right, halfway done, guys. So I just went through all the natural ways that climate has changed throughout time. I went through how we measure it. I mean, there's other ways to measure it, but those are the coolest ones, so those are the ones I'm going to talk about. And some of the things that have happened over time. Now I'm going to go over the anthropogenic changes. What's anthropogenic mean? Human cost. So what are we doing, and how does that affect the climate? All right. All right, cool. You're okay. You're not going to die yet. So anthropogenic causes of climate change. All right, so I'm going to start with the one that we know about the most. So since the Industrial Revolution, what have we done? We've done a lot of what? Revolutioning. Excellent. How about burning fossil fuels? So there's been an increase in burning fossil fuels. So what happens is that there's an increase in greenhouse gases in the atmosphere. We are adding more CO2 than the producers can remove. Who are the producers? Who are the producers? Good. Anything that photosynthesizes is a producer. This is going to increase the greenhouse effect. Sorry. Yes. So the concentration of CO2 in the atmosphere was 280 parts per million for about 400,000 years. And now It's about 400 parts per million. So that is one thing that we are doing. Oops, sorry. Okay, so the next thing that we're doing, deforestation. Whether that's clear cutting or slash and burn, it really doesn't matter. Slash and burn being the worst, of course. Deforestation is going to eliminate the carbon sink and decrease natural carbon sequestration. What is sequestration again? Storage, right? When there's dead plants, after you slash and burn or if you clear cut or whatever, when there's dead, then there's going to increase decomposers. When we increase decomposers, we increase aerobic respiration, which also adds CO2 to the atmosphere. Here's a really important one. I need you to highlight it, write it and highlight it. When we slash and burn the rainforest, or any forest really, what are we adding to the air other than CO2? What's like the most visible thing that we're adding? Ash, right? So particulate matter. So any slash and burn activity increases particulate matter. It also increases CO2, It also increases carbon monoxide. Carbon monoxide is CO, by the way. And atmosphere. I'm going to go over what this does, the slash and burn, what that does to the tundra. And I don't know if I'm going to do that today, but I might. I'm about to flip, so let me know if I'm going too fast. Alright, I'm flipping. Alright, next one is methane. What is one of the sources of methane? Cow belching, right? And then obviously Ms. Johnson has to make sure that she writes the molecular formula there. For those of us that kind of forget it, but methane is CH4. Okay, I'm going to go through all the ways that we can get methane into the atmosphere, so that's more than just cows. Okay, so first one, obviously, from animal agriculture. We just said that. Okay, but also from anaerobic respiration. In landfills. That doesn't make any sense, but think about it this way: when you throw away your food, it has to break down, and when it does break down, it breaks down anaerobically, and it's going to release methane. So landfills are full of methane. That's why they smell the way they do. So that sewage smell, it's methane. Does that make sense? Like, if you ever smelled a landfill, or if you ever smelled sewage, right? That's methane. Okay? Okay. Also from natural gas extraction, we just talked about that. Whenever we're extracting natural gas from rock, some of it's lost to the atmosphere. Flooding from behind dams, or sometimes just a reservoir in dams. Because all that water just sits there, and a lot of anaerobic respiration occurs. We know from ice core analysis that there's been a 70% increase in atmospheric CH4 in the last 270 years. Sorry. 270 years. Okay, comparative to carbon dioxide, is CH4, is the GWP for CH4 higher or lower compared to carbon dioxide? Much higher. Yeah. It actually stays in the atmosphere much longer. All right. Okay, other things. In agriculture, salinization of soil from waterlogging. That can also lead to anaerobic respiration, which can increase methane. So that's more agriculture. All right. So last part. I'm going to go through the first two effects of climate change, and then I'm going to leave the rest for next time. We can talk about the rest of it next time. Yeah. First two effects. Effects of climate change. Okay, so first one is the most obvious one, is rising temperatures. Okay, so the 10 warmest years happened since 1861, happened in 2005. We have, like I just said, atmospheric CO2 and CH4 increasing. This could lead to floods near low-lying coastal areas. Could also lead to droughts. And heat waves. Could lead to more destructive storms. Which then lead to flooding. We could also see an increase in wildfires. Which could obviously lead to habitat loss and extinction. Second one and last one, rising temperatures could also lead to melting sea ice and snow. We know that the sea ice has been shrinking since 1979. We know this because we've got pictures from NASA from space. Like literally less ice since 1979. We have some very massive glacial retreats. What does it mean to be what is a glacial retreat? Sorry. What is it? Is it a glacier going on vacation? What is it? It melts so much that it shifts back. So we have massive glacial retreats now. This can also eat away at coastlines. This can lead to greater runoff because the increased rain. One of the biggest thing is the loss of albedo. Do we remember what albedo was? Good. Let me go ahead and put that as a definition. So what's going to have the highest albedo? Sea ice or land? Sea ice. Okay, so sea ice is going to have a greater albedo. So you're going to have like a lot more reflection off of ice than off of land. It's going to be more wimpy. So this is going to lead to a positive feedback loop. Is a positive feedback loop but a good thing? No. Positive feedback loop means that it's perpetually happening. So if you go home and you eat 5 bags of cookies a day and never work out, right, and you just keep doing it, then your body is going to keep storing fat and storing fat and storing fat and storing fat and storing fat. Like eventually you're going to be like, on my 600-pound life. But anyways, but that's a positive feedback loop. But if you go the opposite direction, you go home and you run 10 miles every day, right? And, you know, you eat less, then you're going to continuously get smaller, right? So you're going to change your body. A positive feedback loop changes the dynamic. A negative feedback loop keeps you the same. So if you just keep doing the same thing over and over again, you stay the same weight, you're in a negative feedback loop. Okay? So you're just coming back to normal. With albedo, right now we're in a positive feedback loop. Okay, so let me write that down. It's really important that you guys understand what that means. Okay, so I'm going to draw a little diagram down here. I think I have space. So increased temp is going to lead to melting snow and ice. And melting snow and ice is going to lead to what? Lower albedo. And then lower albedo is going to lead to increased temp. Because instead of reflecting that light energy away into space, now we're absorbing the light energy. Does that kind of make sense? Guys, I'm almost done. I just want y'all to know that. I know this was like a marathon.
So if we paint like our houses and the roads white, would that work?
I think that would be a good idea, actually, honestly.
Why don't we just paint it?
I imagine that it's more expensive or something like that. I mean, I'm sure there's a reason why we don't do it, but. Do what? That would be probably a good option. But we also probably should start living sustainably too. All right. Just a little bit more and then I promise to be done. So we know that the Arctic summer sea ice is thinning. And something you have to understand about the Arctic sea ice. So here's my ocean, right? And here's my little glacier, not glacier, but iceberg, right? Underneath here is algae. There's algae underneath there. If I had some green, I would color it. But there's algae under there. Algae is going to be at the base of my what? My food web. Good job, guys. My food web, right? So algae is at the base of my food web. And who's eating my algae?
Secondary.
So, yeah, my primary consumer, right? So, like my zooplankton and all my plankton, right? And then something else eats the plankton, and then something else eats that, and so on and so forth. After a while, you get up to, like, the polar bear. But if there's less sea ice, then there's less algae. What happens to the entire food web? If there's no algae, no sea ice and no algae, what happens to the food web? It's destroyed. So there's legitimately less food for everyone. So that also leads to the loss of the Arctic food web. If you're wondering why polar bears are struggling, it's not just because they don't have a place to sit down. I mean, that's kind of an issue because they have to swim and they can't swim that far. But it's also because there's legitimately less food because there's less algae. Okay? So that leads to a breakdown of the food web. We know that the Greenland, write this down, very important. The Greenland glacier, which Greenland is just really one big glacier, like honestly, it's one big glacier, is melting. And that melt is adding fresh water to the sea. So what's wrong with that? Well, it's fresh water. Sea is what? So what we're doing is we are diluting the seawater, which makes it less dense, less likely to sink. And if it's less likely to sink, then it cannot participate in the thermohaline circulation. Remember that circulation in the ocean that brings warm water to the continents? Well, if the water never sinks, then it cannot circulate. So that's what's kind of wrong. I know the Himalayan, I'm just going to write that because I can't spell Himalayan, but the Himalayan glaciers are melting. And the problem with the Himalayan glaciers melt is the fact that that water that is provided, that water is necessary for those individuals in that area. So they use that water. So without that glacier, there are some that will literally go without water. So that means therefore, by the way. And then water shortage leads to a food shortage, which then leads to no water for hydroelectric dams. China has the largest hydroelectric dam in the world. So, and some of that water comes from the Himalayan mountains, that glacier. All right. I'm going to stop there because I know our little brains are exploding, and I don't want your brain to explode. That would be messy. We'll go over more effects of global climate change next time. I want you to consider that when you're firing up your